In this video, we're going to go over some practice problems from chapter 5 of our textbook. Now, starting with section 5.1 here, we're going to be factoring polynomials by factoring out the greatest common factor and factoring them by grouping. So we're going to start with these three examples here. We want to factor out the greatest common factor from each of these polynomials here. Now, in order to do that, we need to pull out the greatest factor that each term has in common in our polynomial expression. So let's look at this first one here, and you might be able to tell right off the bat what factor these guys have in common. Notice that 8 here, just looking at the coefficient of each of these terms, 8 is divisible by 8, and so is 24. So that kind of tells us, okay, 8 might be a part of our common or greatest common factor. And notice we also have 3k's here and 1k here. So both of these terms have at least 1k. So that kind of gives us an idea of what the greatest common factor might be. But another way that we can visualize this is we can split up each of our terms in our polynomial into their factors. So, for example, this first one, we have 8k cubed. So this is going to be the same thing as 8 times k squared, right? This next one here, we know 24 is also divisible by 8. So what I'm going to do is I'm going to split this up into two factors, one of them being 8. So this would be 8 times 3, that gives us 24, and then we still have this multiplication by k. Doing it this way, we can easily see what our greatest common factor is. Our first term has an 8 and a k, and our second term has an 8 and a k. So the greatest common factor in this case would be 8k. And that's exactly what we're going to pull out from each term. So we're going to write this by putting that greatest common factor on the outside of our parentheses. And we're going to write inside of our parentheses whatever's left over when we pull out this greatest common factor. So if I pull out an 8k from this first term, I'm just going to be left with k squared. So that'll be my first term here in my parentheses. And then if I factor out an 8k from the second term, I'm just going to be left with a 3. So I'm going to have plus 3 for my last term in my parentheses. And this would be our final answer. Now we know this is our final answer because we factored this, we split up this polynomial expression into two factors, two things that are multiplying each other, 8k and k squared plus 3. All right, and just to emphasize, our greatest common factor in this case was 8k. Let's look at this next example here. We'll do something similar. We're going to split up each of these terms into their factors and identify the greatest common factor. So for this first term here, we have 7 times x cubed. What I'm going to do is just write this as two factors, 7 times x cubed. And the reason being is because notice 35 and 14 are both divisible by 7 as well. So I'm going to write each of these guys into different factors, one of them being 7. So 35 is going to be 7 times 5. And then we still have this x to the fourth here. And then 14 can be written as 7 times 2, and I also have x to the fifth power. Now, as we can see, each of these terms shares a common factor of 7, but that won't be our greatest common factor because they all at least share 3 factors of x. And we can actually rewrite our factors. So let's rewrite this so it's more obvious. X to the fourth can be written as x cubed times x. And then x to the fifth can be written as x cubed times x squared. So now we can clearly see what the greatest common factor is. Each term shares a factor of 7, and each term shares a factor of x cubed. So our greatest common factor in this case would be 7x cubed. Now you don't necessarily have to write it out like this and do this entire step here. This is just to emphasize what we're doing. We're pulling these guys out and then we want to see what's left over. So if we pull out this greatest common factor of 7x cubed, let's see what we're left with. Well, if we pull out 7x cubed from this first term, we're going to be left with 1. Okay, be careful here. We're not going to be left with 0. We're pulling this guy out, so we're going to be left with 1 here. And we can always check our answer by distributing or foiling. Now this next term, if I pull out a 7x cubed, I'm going to be left with a 5x. And for my last term, I'm going to be left with minus 2x squared. Don't forget to bring the sign with you. Now, like I said, we can always check our answer by redistributing. So if I take this greatest common factor that we pulled out and I distribute it to everything in my parentheses, I end up with our original polynomial expression, which is exactly what we wanted. If I had written this as a 0 instead of a 1, when I redistribute it, I wouldn't have ended up with the original polynomial. Remember, we're factoring this by taking out the greatest common factor, so our expression here and our original one should be equal. So this would be our final answer. All right, let's do the same thing for this last one. Now this one's similar, but we have a bunch of extra factors here. So, or a bunch of extra variables, I mean. So for each of these terms, let's split them up into different factors and pull out the greatest common factor. Now, again, looking at each of our coefficients here, each of these are divisible by 5. So I'm going to split each of these guys into factors, and one of them will be 5. So for this first one, we're going to have 5 times r cubed times s raised to the fifth power. Now, looking at each of these terms, notice that each of them has at least two r's, two factors of r's, and each has at least two factors of s. So what I'm going to do is split up my factors for each of these variables in that way. So what I mean is I'm going to rewrite r cubed as r squared times r, and then s raised to the fifth power is going to be, is going to be s squared times s cubed. We'll do this for each one. 10 is divisible by 5, so we're going to break this up into two factors, one of them being 5. Then we have times r squared times s squared. Here you go. And then lastly, we're going to split up 15 into two factors, one of them being 5. So this will be 5 times 3. And then we have r raised to the fourth power, which can be written as r squared times r squared. And then we have this s squared here. So let's see what our greatest common factor is. Each of these terms shares a factor of 5, which is what we expected since each of these coefficients is divisible by 5. Now, each of our terms also shares a common factor of r squared, which is again what we expected because, as you can see, each term has at least two factors of r. And then doing the same thing for s here, each term shares a factor of s squared by the same reasoning. So this tells us that our greatest common factor in this case is going to be 5r squared s squared. So that's what we're going to pull out from each of our terms. Now doing so, if we pull out our greatest common factor from this first term here, we're just going to be left with r and s cubed. So we're going to have r times s cubed in our first term. Our second term, if we pull out that greatest common factor, we're just left with 2. And then lastly, pulling out our greatest common factor, we're going to be left with 3r squared for our last term here. So this would be our final answer. And again, we can check this by distributing this greatest common factor to everything in our parentheses. So just to emphasize, our greatest common factor in this example is 5r squared s squared, not s cubed. And then same thing for this one, our greatest common factor is going to be 7x cubed. All right, so that's how we would factor these polynomial expressions by pulling out the greatest common factor. Now, for these next two examples, we're going to be factoring these polynomial expressions using a method called factor by grouping. Now, we usually use this method whenever we're dealing with polynomial expressions that has more than 3 terms. And as you can see in both of these examples, we're dealing with these expressions that have 4 terms. So that kind of is a rule of thumb, which tells us we're going to be factoring by grouping. Now, this process is kind of a three-step process. The first thing that we're going to do is group the terms. We want to group them so that each group has 2 terms and each term shares a common factor. Then what we're going to do is factor within those groups. So we're going to pull out the greatest common factor from each term in each group. Then we're going to factor the entire polynomial because after doing step 2, each group now has a common factor that we can pull out. So let's go ahead and do that with both of these examples here. So for this first example, we are going to first group the terms so that each group has a common factor. So we have 10m plus 2n. I'm going to group them as is because they share a common factor of 2. So 10m plus 2n. And then my second group is going to be 5mk plus nk because each of these terms shares a common factor of k. So that's our first step to group these terms. Then our second step is to pull out the common factor within each of these groups. So, like I said, both of these terms in this first group shares a common factor of 2. So I'm going to go ahead and pull that out. And then let's see what we're left with. We'll be left with 5m plus n. All right, now doing the same thing for the second group here, we'll pull out a common factor of k. So we're going to have k on the outside, and we're left with 5m plus n. So that would be our second step. We're factoring within the groups. Now our third step is going to be to factor this entire polynomial, because notice both of our remaining terms shares a common factor of 5m plus n. So what we'll do is we'll pull out that common factor. We're going to have 5m plus n, and what we're left with is 2 plus k. So this would be our final answer here. This is how we would factor that polynomial by grouping. Now, something else to notice here is that it doesn't really matter in which way that you group your terms as long as the groups share common factors. So what we could have done in this example is we could have grouped them in a different way. So let's say I want to group 10m and 5mk. I can group these guys because they share a common factor of 5m. So this is going to be my first group. All right, that means my second group is going to be our remaining terms. We have 2n and nk, and this works because they both share a factor of n, so we can group them together. And now we'll proceed just like we saw above. We're going to pull out a common factor from both of these terms in both groups. So for this first guy, we're going to pull out that common factor of 5m. We're going to be left with 2 plus k. And for our second group, we're going to pull out that common factor of n. We're going to be left with 2 plus k. Now we're going to factor this entire polynomial just like we saw above, but in this case, now they share a common factor of 2 plus k. But that's fine. That's what we're going to pull out from both of our terms. So we're going to have 2 plus k, and then we're left with 5m plus n. And this would be our final answer. Now notice this is exactly the same as what we got before. We just have our factors switched, but this is fine because multiplication is commutative. We're going to get the same answer no matter which way we order these factors here. All right, let's do the same thing for this example here. Now again, our first step is to group the terms so that each term shares a common factor, or each group shares a common factor. So looking at the terms here, we have minus 16m cubed and p cubed. Now, clearly these do not share a common factor, so I'm not going to group them here. But notice minus 4mp shares a common factor with minus 16m cubed. And then this guy shares a common factor with this guy. So that tells me I can group them in that way. So the first thing that we're going to do is rewrite this polynomial like that here. So we're going to have this first term minus 16m cubed, and we're going to rearrange these terms here. So I'm going to have the minus 4mp, and I'm going to swap it with the p cubed. Now doing that, we're going to have our first group here that shares a common factor of 4m, and then our second group here that shares a common factor of p squared. Both of these terms has at least 2 factors of p. All right, so now we know that each group has common factors. We are going to pull them out. So in this first group here, I'm going to pull out a 4m. Let's see what we're left with. We're going to be left with a minus 4m squared minus p. And then for the second group, pulling out the greatest common factor of p squared, we're going to be left with p plus 4m squared. Now, our last step is going to be to factor the entire polynomial by pulling out the common factor here. But notice we actually don't have a common factor. We have a minus 4m squared and a minus p, and this guy is essentially the same thing, just with opposite signs. So this tells me what I can do then is I could factor out a negative from this entire thing, and I would end up with this. So that's what I'm going to do here. Instead of just pulling out a 4m, I'm going to pull out a minus 4m. But we have to be careful with our signs. That's going to change all of these signs here. It's going to make the 4m squared positive, and it's going to make this p positive. Now, when we do that, notice we have a common factor of positive 4m squared plus p. So we can proceed with our last step here, where we're going to pull out that factor. So we're going to have 4m squared plus p, and then we're going to be left with minus 4m plus p squared. So this would be our final answer. And what we can do for both of these examples is we can FOIL and make sure that we end up with our original polynomial expressions. Now in section 5.2, we're going to be looking at factoring trinomials. So these will be polynomial expressions that have three terms. Now the easiest types of trinomials to factor are those where the coefficient of the second degree term is 1. So those are the first two examples we're going to look at in this video. But before we do that, I wanted to show you this example here. Now we've seen in the last section in module 2 that whenever we're multiplying two binomial expressions, what we're going to do is FOIL them. So we're going to multiply our first terms, our outer terms, our inner, and our last terms. When we FOIL these guys, we end up with this polynomial here, and then we're going to combine like terms to end up with this trinomial. So this is the process of FOILing or multiplying two binomials. Now what we're going to do in section 5.2 is we're going to go in the opposite direction. We're going to start with a trinomial of this form here, and we're going to bring it into this factored form. And we know this is a factored form because it's the product of two factors. So we're going to be working in this direction. But before we do that, I also wanted to remind you the standard form of a trinomial. So that is that we're going to have ax squared plus bx plus c, where a, b, and c are going to be integers. A is going to be the coefficient of our second degree term. B is going to be the coefficient of our linear term, x here. And then C is going to be our constant value. So whenever we're factoring these trinomials, the first thing that we want to do is identify what these guys are, what our A, B, and C is. So let's look at this example here. The first thing we're going to do is figure out these coefficients. So the coefficient of our second degree term is going to be A. Let's move this down here. Is going to be A. And like I said, the easiest trinomials are going to be those where A is 1, and that's what we're going to start out with here. So A is going to be 1 in this case. Let's look at the coefficient of our linear term. So we just have this one variable here. So that's going to be minus 11. Don't forget to take this sign with you. So B in this case is going to be negative 11, and then C is our constant term at the end of our trinomial. So that'll be 30 in this case. Now, going back to this example, we know that we're going to end up with the product of two binomials. That's going to give us a trinomial of this form. So we have to get to this. Now, there's a couple different methods that we like to use. I'm going to show you this one here where we're thinking of our degree 2 term. We know that the coefficient of this is going to be 1, and we know that our first term needs to be the product of these two guys. So I'm going to kind of set up our factored form like this already, keeping this in mind. So what I mean is, in this case, we're looking at our degree 2 term, which is k here. And we know that in our factored form, we're going to have two binomials where k is going to be the first term in each of them because we need to get a k squared here. So I'm going to start off with k and k. We know when we FOIL these out, we're going to end up with a k squared. So that's kind of our first step. Now our second step is figuring out what terms go here, or what values go here. Now what I'm going to do is introduce some placeholders. I'm going to call them P and Q. And I'm using this plus or minus here because I don't know what sign I need yet. As you know, when we FOIL these guys out, the signs come with us. Now there's two requirements to find P and Q. The first is that the product of P and Q must give us our C value, or 30. And we know this is the case because when we FOIL these guys out, we know that our last term is going to be the product of these two. Now, our second requirement for P and Q is that these same values must add up to give us our B value. And in this case, that is negative 11. And we know that this is true again by FOILing. We know that we're going to end up combining like terms, just like we saw here. So these guys need to add together to give us this B value. So we need to find two numbers that satisfy both of these requirements here. These two numbers in this case is going to be negative 5 and negative 6. We know the product of these two is going to give us a positive 30, and if we were to add these two together, it's going to give us a minus 11. So we're going to plug these P and Q values into this guy. So we're going to have k minus 5 times k minus 6. And that would be our final answer. We ended up with a factored form of this trinomial, which is the product of two binomials. And we can always check our work let's do that in a different color here, by foiling and making sure that we end up with the original trinomial. So let's FOIL this guy. Our first term is going to be k squared, which is what we anticipated, which is why we set it up like this in the first place. Then our second term is going to be minus k and or minus 6k and then minus 5k. So we're going to have minus 6k minus 5k. Then our last term is going to be negative 5 times negative 6, which gives us a positive 30. Combining like terms here, we're going to get minus 11k plus 30, which is the original polynomial expression that we started with. So this tells us that this is correct here. This is going to be our final answer. So that's how we would factor a trinomial of this form, where the coefficient of our second degree term is 1. Now let's look at this next example. This one is similar. As you can see, the coefficient of our second degree term is in fact 1, but notice we have another variable in this case. We have a w. Now what we're going to do, this is considered a multivariable trinomial. And what we do is we recognize that this is going to be a trinomial in Z. So our second degree term tells us that we're looking at a trinomial with variable z. So we're going to treat everything that's not z as the coefficient or the constant terms in our standard form of our trinomial. So what I mean is, let's identify what our a, b's, and c's are. So as we know, our a in this case is going to be 1. That's the coefficient of our second degree term. Now the coefficient of this term is going to be anything that's not a z. So that would be 8w. Another way that we could write this is z squared plus 8wz plus 15w squared. So anything in front of these guys, this would be our a, this would be our b, and the whole thing would be our c. So kind of jumped ahead there. Our b value in this case would be 8w, and our c would be 15w squared. Okay. So we're just writing this in or thinking of this as our standard form of our trinomial, and we're focusing on our variable z in this case. Anything that's not z is going to be considered our a, our b, or our c. Okay. And we can do this because it's written in the standard form for our trinomial expression. So with that being said, now we can proceed just like we saw with the last example. We're going to set up our placeholders. We know that our final answer is going to be in this form. This would be the factored form of our final answer. And we need to find two values for p and q, such that if we multiply p and q, we're going to get our c value, which is 15w squared. And the second condition is that when we add these p and q values together, we're going to get our b value, which was 8w. So we need to find two values p and q that satisfy both of these conditions. Now these two values then are going to be, p is going to be 5w and q is going to be 3w. Now we can test this out because 5w times 3w is going to give us 15w squared. And if we add them together, we're going to get 8w. So these values satisfy both of these conditions. And we can go ahead and plug them into our p's and q's here. So we're going to get z plus 5w times z plus 3w. And again, we can always check this by foiling and making sure that we end up with the original trinomial that we started with. Now, for the last two examples, in this case, P and Q, I kind of just told you what they were. You will kind of have to guess and check for these examples. An easy way to kind of figure out what these values could be would be to write out the factors of this guy and figure out what can we multiply together to give us this guy, find those values, and make sure that they also satisfy this second condition here. Now, for these next several examples, we're looking at more complicated trinomial expressions in that the coefficient of our second degree term is no longer going to be 1. Now, due to this, we have an extra step before we go ahead and factor this. But we're going to start out the same. We're going to identify what our a, b, and c is. So our a in this case is going to be 10, again, the coefficient of our second degree term. B is going to be 3, the coefficient of our linear term. And c is going to be our constant term. And don't forget to take that sign with you. Now, like I said, there's going to be an extra step before we can proceed with factoring using our P and Q placeholders, and that step is as follows here. We first need to take the product of our A and C. So in this case, it's going to be 10 times negative 18. This is going to give us negative 180. So our requirements for P and Q are slightly going to change, and it's solely because we don't have a 1 in front of our second degree term. So our product of P and Q in this case is no longer going to be C, it's going to be A times C. So that'll be negative 180. And we'll kind of see why once we go ahead and FOIL our final answer. So that's our first condition. And our second condition is going to be the same. The sum of P and Q needs to give us our B value. So that'll be 3. Now, like I said in the last example, it might be kind of difficult to figure out what these values are right off the bat. Even guessing these values might be difficult. So what we can do is we can list out the factors of this guy here. This first requirement is going to kind of lead us into the second one. We need to find two numbers that multiply to give us negative 180. Once we find these values, let's check them against this second requirement. Now, in order to do that, like I mentioned, we could create or list out the factors of 180. Now, what I'm going to do here is called prime factorization. So what we can do is split up 180 into its prime factors. So negative 180 can be split up into negative 2 times 90. 2 is a prime number, so you'll stop there. 90 can be split up into 2 times 45. 2 is prime, so we'll stop there. 45 can be split up into 3 times 15, 15 into 3 times 5. So the factors of minus 180 become negative 2, 2, 3, 3, and 5. So what we need to do is we need to find a combination of all of these factors that, when we multiply them together, we know will give us negative 180, but they also need to add to give us 3. Now, the values in this case are going to be 15 and negative 12. And we can find these values by multiplying all of these factors together. So 3 times 5 gives us 15, and then negative 2 times 2 and 3 will give us that negative 12. Now, again, this is going to be a bit of guessing and checking, but once you factor out this guy here, it kind of points you in the right direction and tells you what you need to guess. So we don't run out of space, I'm going to erase this here, but that is how we get these values for P and Q. P is going to be 15, and Q is going to be negative 12. All right. Now, what we're going to do in this case is, again, we have that our coefficient of our second degree term is not 1. So what we're going to do is we're going to use these values for P and Q and split up our middle value into two different terms so that we can then factor by grouping. So that's the whole idea here for this method. So let's go ahead and do this here. We have 10x squared plus 3x minus 18. Now what we want to do is we're going to split up this middle term into two different terms using our values for P and Q. So we're still going to have 10x squared, but instead of 3x, I'm going to write this as 15x minus 12x, and then we still have this minus 18 here. Now we know that this is true because 15x minus 12x does give us 3x. So we haven't changed this expression here. We're just rewriting it in this way so that we end up with a polynomial with 4 expressions so that we can again factor it by grouping. So the next step then would be to group these terms. So we're going to have 10x squared grouped with 15x because they share a common factor. And then I'm going to have minus 12x minus 18 because they also share a common factor. So what we'll do in this next step then is pull out that common factor. So for both of these guys, they both share a common factor of 5x. Pulling out 5x from this, I'm going to be left with 2x plus 3. So we'll have 2x plus 3. And doing the same thing for the second group here, we're going to pull out a common factor of 6. And I'm going to take this negative with us because notice in this guy, we don't have any negatives. So that kind of tells me that I need to take this negative with me when I pull out that greatest common factor. And doing so, we see that we end up with the same factor as this first group of 2x plus 3. So we know we're on the right track. Our last step then would be to pull out this factor. we're going to end up with 2x plus 3 times 5x minus 6. And this would be our final answer here. And again, we can check our work by foiling. And like I said, it'll kind of make sense why we do this first step here once we do foil this. Notice when I foil this, I'm going to multiply these terms, then these guys, then these and these. So what we're doing in this case is we're taking into account that the coefficient of our x term is multiplying these two values. In the last two examples, notice that our first term here didn't have a coefficient other than 1. We just have a 1z and then a 1k here. So when we multiply these guys, so when we multiply these guys out, we're not taking into account the number in front of it because it's just a 1. It's not going to change any of these values. Whereas in this case, when we multiply these guys out, this 2 and this 5 that comes with this x is going to multiply these guys and change these values. Okay, so that's why we have to do this first step here. Now for this next example, we again want to factor this trinomial, but notice that this is a trinomial of degree 4. So far, we've only looked at factoring trinomials of degree 2. So this is kind of a telltale sign that we might want to simplify this first before we actually go ahead with the steps of factoring it. And we can simplify this by pulling out a greatest common factor. Right off the bat, we can see that each of these terms share at least a factor of 2a's. So we can pull that out. And each of these coefficients are divisible by 6. So this tells me that my greatest common factor for each of these terms here is 6a squared. And we'll go ahead and pull that out from each of these terms and see what we're left with. Now, pulling out 6a squared from this first term, we're going to be left with a squared. From the second term, we're going to be left with 2a. And then from this last term, minus 15. So notice, by pulling out this greatest common factor, we simplified the trinomial that we have to factor. And the coefficient of this guy is 1, so this will be one of the easier cases for factoring. We just need to find two numbers, p and q, such that when we multiply them together, it's going to give us our c value, which is minus 15 in this case. And when we add them together, it's going to give us our b value, which is going to be positive 2. All right, now two values that'll give us this would be positive 5 and negative 3. We multiply them together, we're going to get a negative 15. If we add them, we're going to get a positive 2. So we're going to go ahead and factor that and leave this greatest common factor on the outside. We're going to have a plus 5 and a minus 3. And this would be our final answer. And again, we can check this. What we would do is we would FOIL these guys here. We would end up with this trinomial, and then we can distribute this greatest common factor to all three of these terms here. And we would end up with the original trinomial that we wanted to factor. All right. Let's look at the next two examples here. Now, these are similar, but in this case, what we're going to do is we're going to factor by substitution. Now, notice in this case, we have an n minus 5 squared and an n minus 5 here. So at first glance, you might want to FOIL this, maybe distribute this and see what you end up with. You might get the right answer here, but it's going to introduce a lot of steps and it's easy to make a mistake in that case. Instead, what we can do is we can substitute in a value. So what if I say, let's let x be equal to n minus 5. If x is equal to n minus 5, then we can rewrite this entire polynomial in terms of just this x here. So we have 4 times n minus 5 squared, so that could just be 4 times x squared, since x is n minus 5. Then we have minus 4 times n minus 5, so 4 times x, minus 15. So by doing substitution, we made this polynomial a little bit simpler to work with. And we can go ahead and factor this with the methods that we've seen before. Now, in this case, what we could do, since we have a coefficient of 4 for the second degree term, is we can do what we saw in this example here. We can do this first step. We can find two numbers that satisfy both of these and then factor by grouping. However, I'm going to introduce another method in this example, and this is essentially the guessing and checking method. So the idea here is to find two values that'll make this first term true. So we know we're going to have the product of two binomials, so it's going to look like this here. And I'm going to have a 4x squared as my first term. So that means these two guys, when they multiply together, they need to give me 4x squared. Well, right off the bat, we could say that could be 2x and 2x. That'll give us 4x squared. You could also try a 4x and an x. That would also give you 4x squared. So this whole method is about guessing and checking, essentially. Now, we're going to focus on this first term, this 4x squared. That's going to give us these first two values here. Now, we also know that our C value, this minus 15, is going to come from the product of these two guys. It's going to come from the product of the P and Qs that we found in the last several examples. We have to multiply these guys together to give us this C value. Same idea here. So we're going to guess and check values that we can plug in here that'll give us this product and add together to give us -4. So um, -3 times 5 would give us a -15. So I'll put a -3 and a +5 here. Now what we need to do is check. So we're going to go ahead and FOIL this. So foiling this, we're going to distribute this to this to this, and there we go. We're going to end up with 4x squared. Then we're going to have plus 10x minus 6x minus 15. All right, so combining like terms, we're going to get 4x squared plus 4x minus 15. Now this is really close. Our middle term is a positive 4x, but we need it to be a negative 4x. So these are not the values that we need, but since it's extremely close, what I'm going to do is I'm just going to swap these numbers. It looks like if I want to get a -4 here, then I'm going to need a -10 and a positive 6x. So I'm going to swap my 3 and my 5. So let's redo this here. If I'm going to make it a -5 and a +3 instead, let's see what we get. We're going to end up with, again, 4x squared by multiplying those. Then we're going to end up with a 6x and a -10x and a -15. So we're going to end up with 4x squared minus 4x minus 15, which is what we wanted. All right, so now we essentially factored this trinomial here correctly, but this is not where we end up. This is not going to be our final answer. And the reason being is because, remember, x is n minus 5. So our final answer is not going to deal with x, it's going to be in terms of n. So what we need to do then is we need to plug this value for x minus 5 into this factored form. So let's go ahead and do that. We're going to have 2x minus 5. So we're going to have 2 times x, and remember, x is n minus 5, minus 5. Then we're going to have 2 times x plus 3. So we're just plugging this value for n minus 5 into our factored form. What we'll do next is we'll simplify this. So we'll distribute this 2 to both terms in our parentheses for both of these guys. We're going to end up with 2m minus 10 minus 5 times 2m minus 10 plus 3. This will give us, combining like terms, 2m minus 15 times 2m minus 7. And this would be our final answer. So don't forget, whenever you're factoring by using substitution, we need to substitute this value back into our final answer here. Now, for this next example, we again want to factor a trinomial, and notice in this case, this trinomial is of degree 4. So at first, you might want to pull out a common factor, just like we saw in this example, and see if we end up with a simpler trinomial that we can factor. But notice that none of these terms share a common factor. But what we can do is we can rewrite this guy using exponent rules. So instead of having p to the 4th power, we can rewrite this as p squared squared. That would be the same thing as p to the 4th power. And then we still have our remaining terms here. Now notice, when we rewrite this polynomial like this, we end up with two terms that have a p squared. So this tells me maybe we can use substitution just like we saw in the last example. What if I introduce a new variable? We're going to call it y, and let's say y is equal to p squared. Well, if that's the case, Then I can plug y directly into my trinomial, and I'm going to end up with or y squared minus 10 times y plus 16. So this squared here corresponds to this guy, since p squared is y. So now notice we ended up with a nice trinomial that we can easily factor. We know we need to find two values, p and q, such that when we multiply them together, we're going to get our c value, which is 16. And when we add them together, we're going to get our b value, which is negative 10. Now these two numbers are going to be negative 8 and negative 2. So what we'll do is plug those values into our factored form. We know we're going to have y minus 8 times y minus 2. We know that we're going to have these y's here since the coefficient of this guy is just 1. So this would be our factored form. But remember, whenever we use substitution, we need to plug our original value back into our factored form. So we have this y here, but remember y is p squared. So our final answer would be p squared minus 8 times p squared minus 2. So this would be the fully factored form of this guy using substitution. Now in this last section of our video, we're looking at special types of factoring. So we have four different special types here, and these can be found in our textbook. And the whole idea is to be able to recognize a polynomial of this form and then plug it into its factored form given by these formulas here. So for example, if we have a polynomial that is the difference of squares, so our first term squared minus the second term squared, this can be factored as this here. And we can double check this by foiling. If we were to FOIL this out here, we would end up with this guy. Similarly, we have what's called a perfect square trinomial. So if we have a trinomial of this form and we can easily recognize what our x's and y's are, we can put it into this factored form. We have another version of this perfect square trinomial where we have the difference of these guys here because our second term is negative, and so on. We also have our sum of cubes, which could be plugged into this formula, and difference of cubes. So the whole idea here is to look at these polynomials and be able to recognize what special type of polynomial it is. So let's look at this first example. We have 36m squared minus 25. So right off the bat, notice 36 and 25 are perfect squares, and then we also have this m squared, and we're subtracting these. So this tells me we're looking at a difference of squares. But what we need to do is we need to write it in this form so that we can recognize exactly what our x's and y's are. Our x wouldn't necessarily be 36m squared because remember our whole x is being squared. And y squared wouldn't be 25 because we need to figure out what would be squared to give us 25. So what we're going to do is rewrite this in that form. Notice 36m squared can be written as 6m squared using our exponent rules, and 25 can be written as 5 squared. Now, notice we have a difference of squares. This 6m being squared tells us that's going to be our x value, and this 5 being squared tells us that's going to be our y value that gets squared. So what we're going to do is plug that into this factored form. The difference of squares says we're going to have our first value, that x, minus our y, times that x plus y. And again, we can always check our work by foiling. If I were to FOIL these terms here, let's see what we end up with. We're going to get 6m times 6m, which is 36m squared. Then we're going to have 6m times 5, that's going to give us 30m. Then we have minus 5 times 6m, so we're going to have a minus 30m, and then minus 5 times positive 5 will give us a negative 25. So notice these terms are going to cancel each other out, and we're just going to end up with 36m squared minus 25, which is the polynomial that we started with. So we know that this is the factored form of our original polynomial. All right, let's look at this next example. In this case, we have this binomial here, this y plus z is being squared. And then we have another perfect square. 81 is a perfect square because 9 times 9 is 81. So this again tells me that we might be looking at a difference of two perfect squares. So we have y plus z squared minus 81, which is going to be written as y plus z squared minus 9 squared. So we can again write it in that form of the perfect squares. This entire thing here, this binomial y plus z, would be our x. That's what's being squared here. And then we're subtracting our 9 squared. So we're going to treat this entire thing as our x. So we'll go ahead and write that here. That would be our x, and this 9 would be our y. So factored, it would be our x, so y plus z minus 9, and then y plus z plus 9. And again, if we were to FOIL this, we would end up with this guy. All right, let's look at another example. Now, in this case, we have a trinomial, and notice that this looks like a perfect square trinomial. We have squares for our first terms, and this middle term is a product of these guys and 4 here. So looking back at our perfect square trinomial form, what we need to do is recognize what our x and y's are going to be in this case. Remember, our x is going to be a perfect square. So let's see if we can rewrite that first term as a perfect square and recognize what our x's and y's are. So I'll go ahead and write this down here. A perfect square trinomial is of this form. Yep. So we need to figure out what our x's and y's are. So this first term, both of these guys, 4 and z squared, are a perfect square. And we're going to use our exponent rules to rewrite it. 2z squared is going to give us 4 squared, or 4z squared. Then for our second term here, we need to try to get it into this form so we can see what our x's and y's are. It's already kind of clear to us that our x is going to be 2z, and we have a 4 here. So let's pull out a 2 to represent this guy. And we know that our x term here is going to be 4 or 2z. So we're going to multiply this by 2z. So that must mean our y value is going to be w. And that's going to be confirmed with this last term here. We have w squared, and we know that our last term is going to be this y squared. So we can just write this as w squared. So we can think of 2z as our x value. So this whole thing would be our x, and w would be our y value. So what we're going to do is plug in our x's and y's into the factored form of our perfect square trinomial. That's just going to end up being our x plus y squared. So going back to this, our x is 2z, so it's going to be 2z plus our y value, which was w, and we're squaring that. So that would be our final answer. So that's why it's good with these more complicated trinomials to recognize what kind of special trinomial we're dealing with. Now let's do the same thing with, we have 3 more examples. So with this first one here, notice we're taking the sum of 2 things. And notice our variables here are cubed. So that tells me we might be dealing with a sum of cubes. So we need to see if we can rewrite this guy as a cube. We need to have our first term cubed plus another term cubed. But 24 is not a perfect cube, meaning I can't rewrite this using our exponent rules, kind of like how we saw in this one. 36 was a perfect square, so I could rewrite it like this using our exponent rules. But nothing cubed is going to give me 24. And in fact, nothing cubed is going to give me 81 either. So what I'm going to do in this case then is see if I can pull out a common factor. Notice that both of these are divisible by 3. So let's see if I pull out a 3, what might we be left with? Maybe we'll be left with perfect cubes. So if I pull out a 3, I'm going to be left with 8n cubed for my first term, and for my second one, 27p cubed. Now doing that, we get exactly what we were looking for. 8 and 27 are both perfect cubes. So what we're going to do is rewrite them in this form. So we still have this 3 on the outside. Then we can rewrite 8n cubed as 2n cubed, and then 27p cubed as 3p cubed. Okay, so now that we rewrote our first and second term as perfect cubes here, we can recognize these as our x's and y's. We're going to take the sum of 2 different perfect cubes. So we'll plug them into our factored form here. And let's identify what our x's and y's are. So that would be x, and this would be y. So what we need to do is plug them into our factored form here. We're going to have x plus y, and that's going to be multiplying this trinomial. So let's plug everything in, and don't forget that we still have this 3 on the outside. So 3 is multiplying all of this. So we're going to have x plus y. We said our x was 2n and our y was 3p. So that's going to be our first factored here, this x plus y. And then we're going to multiply it by this trinomial. So we need to plug in our values for x and y into this here. So the first thing that we're going to have is we're going to have our x value squared. So we're going to take 2n squared. Then we're going to subtract out x times y. So that would be 2n times 3p. And then we're going to add y squared. So that would be 3p squared. So what we'll do is we'll simplify this. We still have 3 and 2n plus 3p here. Now let's simplify what's happening here using our exponent rules. We know that this 2 is going to apply to both of these, so we're going to end up with 4n squared. Our middle term is going to be minus 6np, and our last term is going to be 9p squared, again using our exponent rules. Now that's as far as we can simplify this, so this would be our final answer here, factoring this using our sum of cubes formula. Now this next example is similar. Notice we have two perfect cubes. We have n minus q cubed plus 5 cubed. So this is again, we're going to use our sum of cubes formula. So let's rewrite this as two perfect cubes. So this means p minus q, this whole thing would be our x, and this 5 would be our y. So again, what we're going to do is plug in our corresponding x's and y's into this guy here. So we're going to start with our x value, which was p minus q, plus our y value, which was 5. So we're going to have p minus q plus 5. Then the next thing that we're going to have is, again, our x term squared minus our x times y plus our y term squared. So let's plug in these values. We're going to have our x term squared plus minus x times y. And our y was 5, plus our y value squared. So now what we want to do is simplify this. So our first factor here, we can't combine like terms or simplify further, so that'll stay as is. But notice we have this square here. So what we're going to do is FOIL this. We're going to end up with p squared minus 2pq plus q squared. Okay? So this is just the FOILed form of this guy here. Now we also have these terms. Let's go ahead and simplify this. What I'm going to do is I'm going to distribute this 5 to both of these terms here. This 5 is multiplying both of these guys. So we're going to have minus 5p. And then we also have this minus q times 5 here, but this negative is also being applied to both of these. That's also why we have this minus p value here. So we can kind of think of it as like we're distributing this negative, so we're going to get a minus p and a plus q, and then we're multiplying 5 to both of those. So we're going to end up with a plus 5q, and then lastly we have a 25 for 5 squared. And that would be our final answer because we can't simplify it any further. So this would be the factored form of that polynomial using our sum of cubes formula. And lastly, we have another example. And in this case, it looks like we're taking the difference of potentially some cubes. That is a formula that we have up here. We have the difference of cubes, and it's similar to our sum of cubes. Some of the signs are just changed. Now, going back to this, it isn't quite a difference of cubes yet. But again, we can use our exponent rules. M to the sixth power can be rewritten as m squared cubed. And we know that 125 is a perfect cube. And then we have this n cubed here. So we can rewrite this as 5n cubed. Now we have the difference of two perfect cubes. One of them is m squared and one of them is 5n. So our m squared is going to be our x and our 5n can be our y value. So now what we're going to do is plug these in to our formula for the factored form of our difference of cubes. So we're going to start out with this x that we found to be m squared minus our y, which we found to be 5n. So we're going to have n squared minus 5n. Then our trinomial is going to be our x value squared So that'll be m squared squared. Then we're going to have plus our x times y. So that'll be m squared times 5n. And then we have our y value squared. So this will be 5n squared. And again, we want to simplify all of this. We know m squared squared is going to be m to the fourth power using our exponent rules. Then here, we're just going to rewrite this as 5m squared n. And then 5n squared is going to be 25n squared, again using our exponent rules. We can't simplify this one any further, so this would be our final answer. All right, so that'll be it for this video.